you're the newcomer, we've got kind of the standard thing here. We've got a bit.ly URL, which has a zip file. And if you get that and download it, unpack it, and start your notebook server, from there you can get all the stuff we've done here. Okay, so you need to, once you've got them, you need to go into that directory. So I'm going to do that. I'm going to go and do this along with you, basically. So I'm here, and I unzip that MPL. This looks to be needs to be a little bit bigger, doesn't it? Something like that. Is that okay? Or maybe a little bigger still? So if you go into that MPL workshop directory, do one thing here. Okay. I'm going to kill my notebook. So here we are. So you want to start the IPython notebook. And then you want to start it with PyLab mode. And there are two options. We're going to actually use both today. One is called inline, and the other is where the figures will pop out of the web browser because we want to do some stuff with interaction. So we're going to have an inline mode. But we'll start off in inline mode, which means anything we generate in the browser would be popped in. I tend to use this other option, which is no browser, because I don't like it popping up windows for me. I'd rather just type in the URL myself or copy paste it. So once you've got that, that will start your notebook server. It currently has to be started in the directory where the IPy notebooks are, but over time they're going to get a file system navigation built into it. So I mean, they're just working as hard as they can, basically. So all of that will be coming in. We had a long meeting last night where they were talking about where they're going, and they're going to try to have GitHub integration so you can keep your projects on GitHub but pull them into notebooks remotely. And I think they'll be doing a lot of interesting stuff. Everybody here, I assume, has used Matplotlib a number of times. That's why we're in the advanced. You've been to the website, checked out the gallery, basically know that you can sort of click on a plot type and see the code that generated it. So we have hundreds of plotting functions that are specialized for doing certain things. Spectrograms, power spectral densities, error bars, histograms, stacked bar charts. And every scientist or engineer has a different kind of thing they like to do. So I'm not going to concentrate a lot on those because what's really important to one person is totally useless to another one. I mean, I could go my whole life and never make a bar chart, basically, but somebody else might make them every single day. So instead of focusing on those kinds of things, I'm going to try to focus on things that should be somewhat generic to all classes of users. And that's sort of customization, configuration, customizing the look and feel of things, doing event handling, interacting with your figures. And then I'm going to just finish up with a few tips and tricks, like stuff that I do a lot in my plots that I think add a lot of visual appeal or functionality. And so I'll finish up with some concrete examples on some things that maybe are slightly underused use cases. But there's been a ton of new stuff contributed, these Sankey diagrams for visualizing. Oh, that's interesting. I'll try to stay off the web. Okay. So the first thing I want to do is talk about this notebook called Customizing Axes. So you can open that up in V2. Interesting. Yeah. Let me just refresh. I restarted my kernel. I think that's all that's going on here. Or else it's the first law of demos, which is demos always fail. Most people getting that open? Okay. So how many of you have seen a plot that kind of looks vaguely like this in the sense that you got a whole bunch of tick labels that are munged together in overlapping form? This happens all the time in Matplotlib because part of it's our fault for not working hard enough to avoid it, but part of it is some part of the design philosophy that we have, which is I've never liked using Microsoft Windows because I find the operating system tries to help me too much. I don't really want the computer to help me. I want it to do what I tell it to do. And so I kind of designed Matplotlib in that way. I don't want the layout to be very intelligent. I just want everything to go in the place where you tell it to go. And then I want to give you easy hooks for fixing it and making it look the way you want. So by default, and these are things we'll improve a little bit, but a lot of times you get these things where your ticks are too wide or they overlap, and you get up this kind of smushed case here. So what I've done is I've used this new subplots command, which generates a 3x3 grid of axes. And how many of you have used this command? It's relatively new. I mean, relatively being like 2 years old or something like that. Fernando Perez wrote this because he got tired of always saying, give me a figure, and then give me a subplot, and then give me another subplot. And what this does is it creates a grid of axes that have NumPy-like syntax. So once we create that thing, I'm going to create a new cell. Control C, B for below. Control MB for below, and Control MA for above. Now there's two other things that B and A mean.
Yes.
And
before and after.
I'm with you, John.
Is it before or after, or is it above or below? It kills me every time.
Above and below.
Okay. So
Can you maximize your screen just so we see?
absolutely, yeah.
And then
Thank you. And I'll turn off the excess stuff. Okay. So what this axes is it's an array. And it's just like with NumPy, it's a 2D array. It's a 3x3 grid of what are called Matplotlib axes objects. And so the axes is the central object in Matplotlib. It's one of these areas that you draw into. And the figure is this entire thing. So those are kind of the two fundamental objects in Matplotlib. The figure contains multiple axes. And the figure instance here is a Matplotlib figure. Ooh, that's interesting. It has a display hook. And it stores that list of axes here as a list of axes. So that's just some objects that created in there. And you can do NumPy style indexing into these things. So you can have that subplot, or you can refer to the 0, 0 subplot. I haven't mistyped it. Okay. So oh no, I guess it's just linear. It's not. That's surprising to me.
In the axes, big axes, you just call it axes.
Oh, that's the problem. I'm in the wrong place. Yeah. See, I knew I needed you here, Paul. Yeah, so this axes object, yeah, the axes that the figure stores is a list, but this is actually an array object that you can index into it, just like a NumPy array. Okay, so this is a 3x3 array of axes. In fact, it is a NumPy array. And we've plotted this thing, and we've got the typical Matplotlib problem when you have too much on your screen, that we've got a lot of overlapping tick labels. Okay, so the first command that is really useful here to help with this problem are these share x equals true and share y equals true. How many of you have used the shared axes in Matplotlib? Okay, this to me is the killer essential thing to use, and I use it every day. And if there's one thing that you're going to walk away from here today, is I would know how to use these things, and I'll show you what they do. I'm going to have to pop out to the terminal though to make it, because it's an interactive feature is where it's mostly useful. So here I'm in an IPython terminal, and so I'm going to create just some random numbers. And I'm going to create two subplots. So first I'm going to create them this way without the share x convention. And then I have to plot my data. Okay. And I have to draw this because I'm not using PyLab commands. PyLab commands trigger a draw. I'm using the Matplotlib API here, and because I'm calling plot methods directly on the axes. Okay. So most of you use PyPlot. All PyPlot does is it forwards methods to our API, very thin wrapper around our API. So every PyPlot method forwards a call to an axes, pretty much. And so these axes methods have plot commands or mshow commands or set x label, set title. So once I've gotten this thing done, this is our standard navigation window. And you can do the standard thing, pan, zoom, whatever. So that's useful. What I like about the shared x is I'm going to now recreate the same figure, but I'm going to tell it the x labels are shared. So both of these axes will share the same x label. Same plot, and now I just have to up arrow to regenerate. So what this command tells us is any view limit changes that happen on the x-axis on one axis should happen on the other, so they become synchronized together. And it also did something useful here, which it knows that these are the same axes now, so it doesn't bother to draw these ticks. So it's a little bit smart in that way that it says, if you're going to have the same axes limits, you're not going to need the tick labels twice. So already if you're building a big grid where everybody's on the same viewport, turning this feature on will get rid of a lot of redundant tick labeling. So what I like this is now I can go here, and when I zoom in one, I can zoom in the other. And if I zoom to reckon this one, the other one zooms to the same x-axis. But if I move this thing up and down, the other one doesn't change because the y-axis is not shared. So you can either selectively share the x-axis or selectively share the y-axis, or both. So that's a very useful little thing. If you're a subplot user, it looks a little bit different. I'm just going to show you what that looks like. This is the way many people will be using the subplot command. You can turn on the same feature, but you have to manually say share x equals x1. Because it needs to know who to share with. The subplots command builds the grid for you, so it knows who you're sharing with. If you're manually creating your subplots, you've got to tell it who you want to share with. So it's a slightly different syntax. Subplots equals true in the subplots command, or share x equals specify the axes. Okay, so that's the one thing I'd like you to walk away from here today is that. I think you'll find that useful. Go ahead. Okay, so we're back to customizing this little axes object here. So right away on a grid, just turning that feature of sharing the x and y off gets rid of a lot of that redundant tick labeling. So we're partly there in avoiding our overlapping tick label problem. So we've got, nice x-axis ticks and nice y-axis ticks. But, not all data in the world ranges between 0 and 9 on the x-axis and 0 to 1 on the y-axis. So here I'm going to make my data a little bit uglier. So basically, I'm plotting the same data now, but I'm raising my x data to some power of I, and I'm multiplying my y data by by I plus 1. And so now I'm back into the same problem that I've had before. These things are long, they're overlapping. And we have to fix this problem in two separate ways. The first one is with this tight layout that has been written. And this is where I said, I want it to do what I tell it to do, but I want to give you an easy hook to auto do things when you want them. So this tight layout option will basically solve part of the problem for us. What it does is it makes sure that all of the text from one axis will be displayed properly. So it makes sure that this guy doesn't overlap with this guy, and that this guy doesn't overlap with this guy. It will resize all the dimensionalities of the subplots to prevent that overlap for you. But it doesn't solve this problem for us. It doesn't solve this X tick label problem. And for that, we're going to have to be a little bit smarter. But this tight layout is really nice just for generating figures that have a reasonably nice automatic layout. So we're going to try to solve the rest of this problem now. So here I couldn't use the share X and share Y because I really have different scales, right? My Y-axes are different scales. So I've got to I don't have that luxury of solving that problem here. So to deal with this problem, there's basically two things we want to do. We want to use fewer ticks. There's just too many of these things. But we don't want to, you've probably been able to call set x ticks, like give me my ticks here. But that's not a good case generally because you've got to figure out where you want them, and you don't want to have to manually figure out where you want them every time. You kind of want it to happen more automatically. And so what Matplotlib has under the hood is something called a tick locator. And basically this is it's an extensible, customizable class that you can pass in. We have several internally, or you can write your own, that will tell you where to lay ticks out. But our tick locator, the one we use in general, is called the max in locator, which is, I've got a reference to it here in the notebook. And basically that says, give me at most n ticks. At most 3, at most 4, at most 10. And the defaults are pretty high. So I think what we can do with the subplots command to improve it is we should figure out how big your grid is. And the bigger your grid is, set that number to be smaller by default. So if you're a 1 by 1, you might have 10 ticks. But if you're 5 by 5, you might only want 1 or 2 or 3 ticks per subplot. So but we expose that max in locator to you fairly conveniently. So what we're going to basically do is say, hey, I've got a 3 by 3 grid here. I'm probably only going to want 3, 4, 5 ticks per x and per y. And so the function that we use there is called ax.locatorparams. Again, there are two parts that determine how ticks get drawn in Matplotlib. There's a locator and there's a formatter. The locator tells you where to put them. The formatter tells you how to represent that string. So this locator params controls the default ticking, the default tick locating in Matplotlib. And this is the line. Everything else is the same here. We're adding one line, which basically says, for both the x and the y-axis, you could either do it just for the x or just for the y. But for both the x and the y-axis, I really only want 4 bins, which is up to 5 ticks. 3 bins is up to 4, because the bins are the spaces between the ticks. So I want up to 4 bins, and this auto layout call is in the wrong place. It needs to be called once, this tight layout. Okay? So when we run this, we're getting closer now, because instead of having 9 or 10 on each axis, we have 5 to a few. So the Matplotlib is still trying to help you and pick where they should be, but now we've informed it, just don't use so many. So the last piece here is what's giving us trouble are these guys. And these are kind of like in order of 1e to the 4th. These are 10,000. You know, we seem to be handling the small numbers less than 1,000 okay. And we're handling the big numbers okay here too. So this is what's called the formatter. So we just addressed the locator. The locator is the guy who tells you where to put the ticks. Now we're dealing with an issue of the formatter, which is how do we represent those locations as strings. And that's also configurable. And our default formatter is pretty smart, but not quite smart enough every time. So it knows that once you start getting really big, it needs to go to exponential notation. And once you're really small, you don't. What it doesn't know is, in this intermediate range, how close everybody is together. So basically, it has a limit at which it goes into exponential notation. And that default limit is 1e to the minus 7, 1e to the 7. So all we have to do is tell it, maybe over 1,000, at 1e3, I want you to kick in. So the function for controlling the default formatter here is the tick label format. So now we've got one helper function to control the locator and one helper function to control the formatter. And basically what we want to tell it is use scientific limits at 10 to the 3rd. And so now these kick in at a lower resolution, and we get at least something that's usable. So those are the kind of the important hooks for you to make these plots. And I think, Paul, you could do a pull request to the subplots command, right, which detects the grid geometry and basically sets these two parameters intelligently based on the grid geometry. Okay, any questions at this point? Yep, go ahead. To how to configure that itself, like what the format string is for that thing? We'll find out. Okay, so let's take a look. Off the top of my head, I don't know the answer to that, but I'll show you how to kind of dig into there, and we'll take a look and see how to find out. So I'm going to create a new cell below. And so I want to get my hands on that formatter, basically. And where it lives, we'll look at the x-axis formatter. So first thing, I've got this ax. That's defined from my session above, so that's just the most recent axes I was working on. And then there's this function called getMajorFormatter. And that just returns the instance that does the work. Okay. So the x-axis has a major formatter and a minor formatter. Major is the major grid lines, minor is the minor grid lines. and then the y-axis has the same. So this is the guy who controls that representation. So I'm going to just inspect that for a second and see what's there. Okay, I want to see what this is, the format. It's a string. Format.
And it's a string with %1.
Oh, you printed it? Okay, so that's the guy right there who seems to be doing. That's for the. But that's interesting because that doesn't seem to be what's being used on the x-axis, is it? I mean, those are not 1.0 formats. I'm kind of a go to the source code kind of guy, typically. So I'm just going to pull this up.
Because what I'm thinking of in particular is that there have been times that I've basically rewritten the formatter myself. So
Sure.
I can get a nice LaTeX times 10 to the 8
Yep.
instead of 188.
Mm-hmm.
There's a cleaner way to do that.
So the cleanest way would be this guy. If that's what you're looking at right there, is use math text equals true or false. So let's just see how that field propagates down into our code. That sets it internally. I don't know if we expose that to the user. Set scientific, set power limits. Format data short, format data long. To whether or not to use that or not. So you can change your default. I'm going to do something that we shouldn't do, but I'm just going to try it to see if it works, is I'm going to set that private variable. So I'm going to say format. I just want to see if we can hook into that. That's why, I mean, it's Python, right? We're all adults here. So we should probably make that expose that a little bit better to you. But one of the comments was you can expose it using the config file, which we'll be talking about in a little bit. But you may not want it to be true all the time. But I guess the point is we do have access to those RC params in code here. So that's the other way to do it. Would be exactly. So, yeah. So does anybody know the name of it? Okay.
Is what it uses.
Oh, it does use that?
Yep.
Like this? No, it's not useTech that I want, because I'd rather use Matplotlib's internal math tech rendering. Is that what it uses for that value? Are you looking in the code?
Yeah, it only uses that value.
Okay.
Oh, sorry, yeah. I don't think the RC param is the only. That's
Okay.
the only one that is used. And
Yeah,
they're
that's
not-
see. Matplotlib has two ways of rendering mathematical text. One is our internal mathematical rendering engine, and one is the external LaTeX engine. Here it's calling out to the LaTeX engine, and it's not rendering right on my system. It may be something to do with the downsampling. I'd have to look into that. We should be using our internal math rendering engine for that kind of thing. Okay, so you can hook into these things, but there should be better ways of hooking into some of that. You could create your own instance and set it. That's the other thing, is you can say ticker dot, and then just set use tech equals true. That's the right way to do it probably. So it would be right here, x dot x-axis dot set major formatter ticker dot scalar formatter use tech equals true. Was it use tech? I'm trying to. I'll take a look at it in a second. Give me 1 second. Camel cased.
Yeah.
So you can instantiate this guy yourself. Text? Possibly?
Text, yeah.
That's a big traceback. Oh, because the RC params are still set. Remember, we set those RC params. That's a global setting. So I need to unset that. Who made me go off the reservation? How do we spell that?
Use tech.
Use tech. Okay.
Text use tech.
Okay. So we've turned that back off. Now we're getting math tech rendering. So that's sort of the code way you could hook into that process. Okay. Since we were just talking about the RC params, I'm going to jump into your question real quick. And his question was, if I'm producing figures in different kinds of environments, maybe sometimes for a certain journal, maybe sometimes for interactive scripting, maybe sometimes for a user interface, and I want to customize the look and feel of those different things, how can I do that? So I'm going to jump out of the notebook for a second and just show you briefly how you would do that. The first place is you need to hook into our what's called our RC file, and where you would find that on our website would be in the docs section. I mean, one of the easiest way to find it is in the docs section. There's a customizing Matplotlib section. And that tells you, okay, I have you now, Luke Skywalker. Okay, so this is just my local build tree of the docs. This tells you about the Matplotlib RC file, which is about what we're about to talk about. And it's just a simple key value pair file that has the default configurations. Here, earlier we were setting them in code, but you can set them in the config file. And this is a sample, so you can download that file to your system. And basically, you can either put it in the Matplotlib default config directory, which is .matplotlib, or you can put it in your local directory. So Matplotlib will pick it up and in your local directory. So that's basically how you do this. So the way this file works is everything is commented out except for the back end. So you basically, because we want to have a little bit of flexibility to change these, and so it's good if you only uncomment the defaults you want to change. So I'm just going to copy this file. And throw it into my Emacs buffer. So I'm going to go to the talks, PyData, MPL dir, MPL PyData. Yep. And I'm going to make two directories, temp1 and temp2. And I'm going to drop this file called Matplotlib into both of those directories. So that I'm dropping in temp2, and I'm also going to drop it in temp1. So this is a large file, and basically almost every aspect of the figure can be controlled here. Tick size, tick length, font size, font color, italics, the background of the axes. So I'm going to just tweak one thing so that we don't spend a ton of time here. I'm going to say the axes face color. So the default, this is the axes, this is this region here. That's white by default. For publication A, I'm going to make it blue. And for publication B, I'm going to make it red. Now, any code that's run test.py. Thank you. I'm going to cheat here because I'm in a big hurry. Don't try this at home. We try to get people using pyplot. So I'm going to create the same thing, and then I'm going to save this in temp1 too. Okay, so now we've got the same script in two different locations, basically. Actually, you know what? We only need one script. We just need to run the same script. So I'm going to delete it from temp1, because the idea is you want one script, right? Right. So I'm now just going to navigate on the file system, temp1. So that's where my matplotlib.rc lives, and I'm going to run the script that's in temp2. Should be a show at the end, huh? Oh, the thing is, because I commented out the back end, I actually have to tell it the back end I want to use. So I'm going to, by default, if the back end isn't set, it goes to one of our image backends, so nothing happened. Okay, so that's the background there. But now if I run the same script from temp2, I get red. So you can pretty much customize the look and feel of all these things using that methodology. And how many of you are R users? So as part of this exercise, I was looking at some ggplots that Wes McKinney was making today. And I just wanted to see how we would do emulating the R style. So here I've just written a little bit of a section of code, basically setting my axes face color to be gray and my tick labels to be white, and changing the default spacing between. All of these are configured at the RC level if you want. I've configured them in code in this example, but you could set your config file up to look like R if you wanted to. We initially set this thing up to look like MATLAB because I was writing MATLAB emulation mode. But again, I think it might be nice to expose a little bit of these things at a higher level as well for people who want to say, give me this config. You're saying, can we borrow from somebody who's already developed these styles? There's not. There hasn't been a file exchange, or people haven't submitted these kind of style files, if you will. Right. Or the other option would be in module code, essentially, we could have styles which instead of, it depends on whether you'd rather make a function call or drop a file, right? We could have rc.set rstyle, and it just sets all those parameters. So you could call that function in software, and then you could actually toggle within a session to go from rstyle to MATLAB style or some other style. But no one's ever suggested such a thing, but we could certainly have some entry points to that.
Yeah, I mean, there's
On how that's done. So you can look and see. I don't think we need to go through everything that's in here, but basically these are just these are a bunch of API calls that sort of show you the Matplotlib, our hierarchy and our API. This is the way I write code. I don't use the PyPlot interface very much, and it's another thing to just show you. If you want to sort of write more Pythonic code, all of these API methods are available to you. I was a C++ programmer before I was a Python programmer. If I had to do it all over again, these would be properties and not setters and getters, just to make that slightly more Pythonic. Right. So if they're just properties, then you
don't know if it's a method or whatever.
So you're old school like me.
No, I'm just saying it has advantages.
Yeah, so ax.x-axis. Let's just say ax.tab, just to give you a flavor of how many of these things are out there. So I'm still on the A's. So there's a fair amount of stuff you can set here. And we have, I would say, all very good doc strings. So unlike Guido, we have good interactive doc streams. So if I say set x label, you'll get something that looks like this. It basically says, set the label. There's a dictionary to control the fonts. And these are the keyword arguments. And here's basically every argument that you can set. There's quite a few. It tells you the name, what they can be. So every doc string we have pretty much has this level of detail in terms of what you can do with it. So there's a lot of stuff in there. I mean, the font weights here, can be in. So this is basically, is it bold or is it not bold? These are your options for setting how bold your text looks. So there's a very high degree of customizability under the hood if you want to go down that path. I'm probably going to switch gears now, even though there's a lot more in here. But that's the great thing about a notebook. You guys can read this on your own time if you're interested. I'm basically kind of going through some of the stuff we already did, how to set your own formatters, how to set your own locators, how to do really stupid stuff like rotate your tick labels and make them red, just kind of showing you the API on how to drill down and get into these things. This is some, I want to talk a little bit about this because this is probably something most of you either haven't used or are not familiar with, but is really nice. Have any of you used JJ's Axes Grid or Grid Spec stuff? A couple of you. JJ's an astronomer. He's a really talented Matplotlib developer. He's the guy who's done, if you've looked on the gallery, sort of what I would call most of the eye candy, these fancy arrows and fancy boxes and all of that kind of stuff. He's done a lot of that work. But he's also done an awful lot with grid layout, like how to do sophisticated grid layout. So the Matplotlib subplot is by default a regular grid, m by n. But a lot of times you may want to specify something like this, where you've got a big axis, something above it here and something above it here. You can do that manually with your axes command. You can say left, right, left, bottom, right. No, it's left, bottom, width, height is the syntax. But there's a lot of arithmetic to calculate exactly how you want this to be. So what he's done is, if you've done any GUI programming, is he's basically implemented the concept of a span. So this is a 3 by 3 grid. So this is basically your 3, 3 here. He's got a 3 by 3 grid, but it has a call span of 2. So that basically says this is the 0 guy, but I want you to span 2 columns. So the first one is ax1 here. So basically he's saying, and when he did this, Matplotlib uses this 1-based indexing, like subplot 1, subplot 2, figure 1, figure 2, which is very unPythonic because Python is 0-based indexing. But again, I was emulating MATLAB at the time, so MATLAB had a 1-based convention. When JJ rewrote this, he's like, I'm not going to continue to perpetuate that idiocy. So he redid this with 0-based indexing, so that's one mental mapping that you'll have to make. This is more Pythonic. But as you'll see in a second, he also wanted to support this with axis slices. So I'll show you that in a second, but he basically, you can slice these things to create spans. So what this is basically saying is for axis 1, which is here, give me a 3 by 3 grid. This is first row, 0th column. So this is this guy. And span 2 rows. This is spanning 2 columns and 2 rows. Axis 2 here is the 0, 0 guy, so he's the uppermost guy in the array. And he spans 2 columns, but only 1 row. And this guy here he's the 1, 2 guy, so row 1, column 2, which is the last column because it's Python-based, and it spans 2 rows. So this enables you to lay things out nicely. So the example I gave above is similar, looking at it like a marginal distribution of a 2D histogram. These are the kind of layouts that are useful for those kinds of things. And he does, so this is an example showing the same thing. You can actually create one of these grid specs and you can do slicing on them. So you can express a span here, like this span on x2. You can express that as an array slice. So starting at 0, going all the way up and not including the end, right? So he's basically expressing the spans here as slices of a 2-dimensional array. So just like you have NumPy slices, give me the first, up to, and you can do the -1, so, the last row, but the second to last column. So it's kind of a nice thing, and he's perverse enough that it goes even more deep than this. I'll show you one example where he does this thing. So there's a documentation page called Using Grid Spec. So this is just that example I just showed you. But it turns out, like this guy here is a more complicated one. Once you've got one of these, you can put subplots within subplots. So he defines one of these grid specs like this, but then he starts sticking. This is a 1 by 2, and then he sticks these. You can put geometries within geometries, basically. So you can recursively specify these things. So he does things with Matplotlib which should be illegal. Yeah, so here he's basically using his grid specs from above that he created, but he's sticking them in a 1x2 grid arrangement. So he sticks one in the first one, he sticks this other layout in the other one, and they all kind of lay out nicely. So if you need to do sophisticated layouts of axes, he's your man. Okay, so I'm going to shift gears here and do some event handling. The next section is basically going to be interacting with your figures. Mouse clicks, keyboard events, selecting data, picking data, that kind of thing. And in order to do that, I'm going to restart my notebook server because everything so far has been into the browser. And here I want to actually pan and zoom and click and interact. So I actually want the old school Matplotlib figures to pop out so I can interact with them. There's a lot of talk about how to get interactive figures into the browser, but that's a development project. So for right now, the figures inside the browser are static, but we can, most people interact with their figures through the standard Matplotlib window. So in order to get that, and if you want to follow along, you basically just need to kill your notebook kernel. And then I'm going to say, instead of PyLab inline, I'm just going to use the TK backend. And so that just tells the notebook, use the TK backend, pop the figures out, and you can interact with them. And if you've done that, you also need to refresh this page, because this page is still talking to the old notebook kernel. So simply refreshes it. It's the same URL for me, so it's going to point to the new. And the workbook we're going to be dealing with is called MPL events. How many of you done any GUI programming, event handling? Most of you. How many of you done any event handling in Matplotlib? A couple. Paul wrote Pong in Matplotlib. We have our own event model, and just like we support user interfaces in Qt, TK, WX, native Mac OS X widgets, and some FLTK that you've almost never heard of. And so we have to support user interfaces across many different windowing systems. And so we have a Windows system agnostic drawing API, and we also have a Windows system agnostic event API, so that if you write a new backend or a new windowing system comes out, we don't have to redo all that work. So when you interact with a figure in Matplotlib, you're doing it through our event system. So basically all of the interactions are written using Matplotlib events. See if I. So there's some standard keyboard events like G for grid. You can turn that off. We're trapping the key press and exposing it, or I can type L for log to toggle logarithmic axes on and off. Or I can type S for save, and it should pop up a save dialog. Not implemented on this backend, apparently. But we expose that event handler to you so you can write your own events. And the advantage of doing it that way is that you can send your code to another Matplotlib user who might be on Mac OS X, and the same event model will work. That's the basic advantage there. Kill that. It's MPL widgets 3. That's what I'm going to be working with. MPL events is a perfectly good worksheet. There's a couple here, and I'm not going to do it all, that were written by Fernando and Paul. While I'm on the subject, I think I'll just show you Paul's because it's kind of cool. What he did here was he took an XKCD plot and said, how can I make this in Matplotlib? That was his goal. And so it's a nice long tutorial. Oh, do I have to do run all? You saved it without the output?
I think I do set PyLab inline in the beginning. Did I?
Oh. So there's going to be a lot of stuff popping out. Okay. Well, I don't want to, yeah, you do set PyLab. Oh, that may be confusing the kernel.
Yes.
I'll worry about that at the end because I've set my kernel to pop out and he's setting it inline. So I'm going to just actually restart my kernel. But it's a nice little demo. You can look at it later as you have time, where he basically replicates the XKDC figure in Matplotlib. Okay, so I've got to now maximize this so you can see what we're doing. So this is sort of the basic event handling model that we have, where the Matplotlib figure has a canvas. That's sort of your GUI canvas. And it has a connection method where you can connect to one of many Matplotlib events. And there's a tutorial on the website called the event handling tutorial, where these will be listed for you. There's a key press event, a button press event, a mouse motion event, the kind of the standard GUI events. And the way it works is you connect the event to a callback function. And every time you press this key, any key, this function is called. And we try to keep it pretty simple, so if the event has a key field. And so what happens is when you press this, whenever you press a button, it should print you've pressed this key, and then it looks for, this is key handling. If the key is X, what we're going to do is toggle a line's visibility. So on this example, I'm plotting 2 lines, and every time you press X, I want you to turn one of the lines on or off. So I ask, is the line visible, by calling the line's getVisible property. Everything in the Matplotlib figure has this property. Every tick, every text has this visible property. It's the base class's method of artist. And then I can set the visibility to not visible. So that's sort of the toggle operation. And then I have to force the figure to redraw itself. So that's sort of a very simple event handling loop. And let's see if I can run this from. Okay. So there's my figure that pops up. I've plotted 2 lines, and I just press X. And in the notebook, it should be saying you pressed X. Let's see if it does. Okay, so it's saying you pressed X. And every time I pressed X, I toggle a line. So that's sort of a very simple way of connecting to the low-level key press events. So as I said, we have several of them. The most important ones are key press, button press, and mouse motion, called motion notify event. But most people don't want to wire up really low-level GUI code themselves. So we've tried to encapsulate some of the common things that people want to do with mouse interaction into what we call widgets. So these are little tools that we've written to do kind of basic stuff that you might want to do in a figure. So we have a module called matplotlib.widgets. And I'll show you one of these in action, and then I'll show you where you can find more. So this is a sort of a standard cursor widget where as you move your mouse, a cursor will follow you. So basically, I'm just creating some random data, and I instantiate this cursor object. It has a color, it has a line width, and this blitting is kind of a rendering feature that does optimizing rendering on backends that support it. Mac OS X native backend does not, so if you're running that, you may encounter it. So you would want to set useBlit equals false if you encounter any problems with it. So that's interesting. It's failing. Oh, I got a traceback. Oh. I didn't execute that line. Those are the kind of errors I like. So that just gives me a little cursor widget as I'm following along. And I'm getting my XY coordinates as usual down there. So the cursor is not that useful. The multi-cursor to me is actually useful. So the way the multi-cursor works is you can create as many subplots as you want. And you basically have axes 0 and axes 1, but you can create as many of these as you want. You initialize this multi-cursor with the figure canvas. Every figure will have this canvas instance. It's our abstraction of the GUI. And you give it the list of axes that you want to share this cursor on, and then you set your line properties, as we did before. So what's useful here is when you have 2 data sets, and you want to look at events in one and see how they're registered to events in the other. So that's, I think, a lot of times useful because you have like 4 or 5 of these panels, and you see a feature in one when you have the same axes limits, and you want to zoom in on that and see precisely where you are. So it just gives you a visual alignment there. We have a lasso widget, for selecting regions. So this was kind of a nice little example. How many of you made one of the pandas talks? Okay. So what I wrote here was a little pandas widget viewer, basically. So in the scripts, I'll kind of walk you through what this thing does. But the idea here is, you might have a data set that has multiple types of data, some of which may be strings or categories that not easily represented on your graph. And a lot of times what you might want to do is plot value 1 versus value 2 on a scatter plot. And then you see some outliers somewhere, and you want to say, hey, what's going on with those outliers? How do I drill down into those outliers? So what are they? What days did they occur on? What was the other values that are not on my graph? So sort of hover over a region and inspect that region. That's kind of what we're trying to do here. So what we're going to do is plot 2 of our values. We read in some financial data from a CSV file, do some standard pandas stuff, attach a new column, and print out some of it. So this is, as you can see, the daily pricing data from the stock crocs. So I loaded up this little pandas data frame. And so I want this to be kind of generic, so I'm going to specify which pandas fields I'm going to be working with as strings, so that throughout the code I can refer to these things. So I'm basically going to be working on the x-axis with volume, which is the daily trading volume, and on the y-axis is the daily return in percentage terms. I'm going to have a single axis and plot, this is the data frame axis, the x field column versus the y field column, and as a marker plot. So it's basically a scatter plot. Okay, so it's just going to be a 2D scatter plot. Now this is one of our widgets called a span selector. And what the span selector does is it lets you just basically select a horizontal or vertical region of your plot. It's like a rectangle, like a zoom to rectangle, but it's only one of the dimensions of the rectangle. So what we call a span, like a region of the x-axis. So this is a pretty simple one, so I'm starting kind of with the easiest one. And I'm going to basically say, when you select a region, call this function onSelect. So this is sort of the standard callback mechanism. Call this function. Some of these are just sort of drawing things. It's going to draw rectangles that are red and translucent. So these are the rectangle properties that we're going to draw. This is where the action happens. We're selecting what, again, a span is an xmin, xmax region, so we're going to be selecting a region. It's going to print the region we selected. It's going to get the same x field that we plotted, so it's grabbing that guy there. And it's going to do a Boolean mask where x is greater than xmin and x is less than xmax. So it's selecting the region. It's selecting the data in that region, and then it's just going to print it to standard out. So this prints the entire data frame. So we have an XY scatter plot, but we're just going to be looking at the data in that region. Let me run it one time so you can kind of see what it looks like, and then maybe we can take some questions if there's what's going on in the code. So this is the XY scatter plot, x field versus y field. And so basically, we have a lot of data around here, which are small volume days and kind of, some sort of distribution of returns around those days. But we also have a few outlier days that we might be interested in saying, these were really big volume days out here. What did the rest of the data look like over there? So that's where we select that region, that little rectangle that I just selected. And that triggered our onSelect event here. So what happened now is we got this standard output back from the terminal. This was the data between xmin and xmax inside this region. So here we can see the outlier events that happened on those days. So it's kind of a nice way of interacting with your data. I'm going to try that again. I'm going to try to go over here and just collect the very 2 biggest days. So that's my span that I'm selecting. And when I release the mouse, it triggered another print here to my screen. These are the 2 events that I selected. So it's an easy way of drilling down into your data. So I accidentally probably selected the whole data set just as I was trying to close the window. This is exactly the same thing, but it's using a different widget. It's the rectangle selector. So zoom to rect is a very common mode of interacting with data. We give you a widget so you can hook into it yourself. So if you want your own rectangle tool, you just create one of these widgets. There's a lot of arguments, but you don't need all of these. These are just options. Sometimes when your rectangle is too small, you just click your figure and your rectangle is too small. You want to ignore that. This is basically saying if your rectangle is smaller than some minimum rectangle, ignore it. So these are just some extra options, but it's exactly the same selection code that we had before, except now it's a two-dimensional selection. We have the x1 and y1 of where the upper corner of the rectangle was, and the x2, y2 of where the lower corner of the rectangle was. So we get that. And to do the mask, we have to make sure x1 is less than x2, because I want to basically say this operation where x is bigger than x1, less than x2, y is bigger than y1, less than y2. So this is just a toggle, make sure that x1 is always less than x2. I get my x and my y fields, apply two-dimensional mask, and then I select that region out of pandas. So it's same logic in 2 dimensions now. And so we should be able to, now we could go in here and try to get one of sort of a denser area. I did a tiny rectangle in there, and it shows us what we get. So I should be able to grab these 2 points like that. So you can hook into a lot of these widget tools, and I hate to say write once, run anywhere, because it reminds me of Java, and that was the failed promise of Java. And I'm not going to promise that you won't encounter some glitches across some backends, across some platforms. But for the most part, the event model is the one we use internally for panning and zooming and doing these things. So to the extent that those things work, the event model should work reasonably well. Okay. All right, so I'm going to, even though Paul told me I don't have to do it the old school way, because I don't have a lot of time and I know how to do it this way, I'm just going to kill my kernel and go back to inline for the last segment I wanted to talk about today. The last one is called MPL recipes. Oh, I have to refresh. If you kill your kernel and restart, because I went back to, I have to refresh this mode. So these are just going to illustrate a few different kinds of plotting commands that I like to use. That some of them are in the eye candy realm, just making plots look a little bit more attractive. There's a command I like to use called fill between, where the syntax of it basically is, given time, or your x-axis, fill the area between ymin and ymax. And these can either be a constant or an array. So if they're an array, it basically will fill between the ymin and ymax as an array. And if it's a constant, in this case ymin is the constant, 1, it fills between a solid line. And you can set some parameters just to create shaded region plots. So that's a pretty easy thing to do, but it has a nice argument to it called where that to me makes it pretty interesting. So this is an example that I've used to show how you can use the where argument. In both cases, I'm filling between the 2 arrays. I'll show you how I created these in a second. But I'm filling between this array y50 and y200. So this is a case where both ymin and ymax are both arrays. And it just creates the polygon between them. And I can give them the same arrays in both cases, but I can give it a Boolean mask here that says where some condition is true. So this is a random walk that I've set up here. And it's the same random walk from above. So basically, this is my random walk. It's a geometric random walk where I take 1 plus some random number, cumulative product. It's what Wes called the total return on $1 invested in his pandas talk. And these are 2 different moving averages of that variable. So you can compute a moving average in NumPy as a convolution. So if you convolve your variable with a weighting function, that's essentially the concept of a moving average. So you could do an exponential moving average if this was an exponential function, or an equal weight moving average by giving it an array of 1s. To make it a proper average, you need to divide by 50 so that the total weighting is 1. So here I have 200 ones weighted by 200. So I do this convolution. The convolution has sort of a decay part at the end, so you want to just extract out the beginning part. And at the beginning, there's an artifact where it's a moving window, basically, the way the convolution works. So at the beginning, it's only the average of 1 point. So these points aren't really valid averages because it's 1/50th of 1 point And so you basically, what I'm doing is saying for the 50-point moving average, I'm going to just say that's bad data. For the 200-point moving average, I'm going to say that's bad data. But then a very simple measure of trending that, kind of the simplest measure of trending that people in the financial industry like to look at is whether a short-term moving average is higher than a longer-term moving average. So here I'm creating a logical array saying, I'm going to say this thing is trending up when the short-term moving average is greater than the slower moving average. It's a trailing, because the moving average is a trailing indicator, it's a trailing indicator. So what I'm doing now is I'm basically coding these different regions so I can see where my moving average is positive, where the short term is higher than the long term, and where the short term is lower than the long term. So these basically show you kind of one example of how you can use these fill-betweens to put extra data onto your graph in a way that conveys a lot of information. I like to use, whenever I use these polygons, I find these colors are too stark. So I like to soften them with alpha. Alpha is the transparency channel in Matplotlib. So anything that has an alpha less than 1 you can see through, you can see what's behind it. That's not so important here because these are disjoint regions. You don't need to see through them. But there's a secondary effect of alpha, which is that they just soften colors. Oh, that's weird. What was wrong? Oh, did I not execute it? So this is an example when I was talking about softening the colors. This is the standard blue. If you take that away, make that alpha, 1.0 is the default. It's just a much stronger color. So I like these like kind of soft pastel-y colors that you can get out of setting alpha equals 0.1. So this is, again, just to kind of, for the visual enhancement of your figures, I find tweaking that alpha a little bit can give you different kinds of feel to your colors. This is a slightly more involved example where what we have, it's actually quite nice, an illustration of how powerful NumPy is as an expressive syntax. What I'm doing here is I'm doing a random walk simulation with 100 different random walkers, and each random walker is going to take 250 steps. And I want to do some statistics on the population. Like so what is the average position of the random walkers? And what is the variance of the average position of the random walkers? So I want to take 250 steps, and basically I'm creating a random distribution here with different means. So my mean of the first population is 0.02, and my mean of the second population is 0.04, so they're going to be walking a little faster. Both of these random walks have drifts, basically. So this is the drift term, and this is the variance term. So my first population has a smaller standard deviation than my second. So these are two-dimensional unit normal distributions with a different mean and standard deviation. And all we have to do to compute the random walk is this step, which basically says, give me the cumulative sum of the walkers and sum over dimension 0. So with NumPy sum on a two-dimensional array, if you just call sum, you get the sum of all the elements. Or you can sum over axis equals 0 and just get the sum over over the 0th dimension, or you can say sum over axis 1 and get the sum. So what we've done here in 6 lines of code is a complete simulation of 100 random walkers taking 250 steps. I'm going to insert control M. Okay. So at the end of all of this, I've got something that comes out that looks like that. It's still 100 by 250. It's still 100 random walkers. And I'll just plot one of the trajectories. So this is the first random walker in x1. So here he goes, and because it's got this positive drift term, he starts to take off. And in Matplotlib, you can also slice this guy. So you can, for example, say, show me the first 5 random walkers. So you can pass these array slices in, and you'll get the trajectories of the first 5 random walkers. So that's, and I think we have 100 total. So what we want to now do is compute some statistics on those random walkers, which basically says, give me the average position over time of all the random walkers in population 1, give me the standard deviation of all the random walkers in population 2, and do the same thing for both sets. So we've got 2 walkers, different variances, different means. So here again, 4 lines of code, we've got population statistics. So again, you know, that's why NumPy, MATLAB, and all this family of languages is so good for this stuff. So for the last thing, I just want to plot the result set. And again, I'm illustrating this fill between using shaded region. So basically, we can see the population mean, which I'm plotting here as t times mu1 and t times mu2. And you can see the population variance here. What I'm computing is, well, it's mean plus 1 standard deviation, mean minus 1 standard deviation. So what we're seeing is the 1 standard deviation from the mean of the population over time. So population 2 had a bigger mean, so it's climbing faster, but it also had a bigger standard deviation. And so it's got a wider distribution of outcomes. So this is the 1 sigma probability density function over time of the random walkers, basically. So we're viewing slices of this. And again, using the fill between with an alpha channel, we can see both populations. Even when they overlap, you can see through them. So it's a nice little technique. And you know, we expect the variance to grow linearly with time for population of random walkers. So we expect the standard deviation to grow as the square root of time. And that's basically what you see here is a standard deviation function that grows as the square root of time. So I use fill between a lot. I think that's a nice little helper function. Another one that I like for is kind of these text boxes. It's very easy to create around any text in the figure, just a little box. And I think it draws attention to it. It makes your figure a little bit richer visually. I'm normally against most forms of what Tufte calls chart junk, but I think some of this stuff adds a little bit of visual appeal. So text is a generic command. I'm going to turn this off. So this would be a standard text command. The rest of this is just a histogram. So I've got a long mathematical expression saying in LaTeX, the mean is this, the median is this, and the standard deviation is that. And we have this support for new line separated text. So one text command gives us 3 different textual representations. And this is actually a very useful technique here, which basically says, place this thing in axes coordinates, not data coordinates. So rather than try to figure out, oh, I want this thing to be at, because the normal coordinate system is data. So this is like, in data, this is minus 125 versus, you know, 550. So you have to figure out where that, if you want it in the upper left, you have to figure out what is it for this data set, hard code that in. If your data changes, it's suddenly in the wrong place. So we have a number of different coordinate systems, but one of the most useful one is this axes coordinate system, where you can say, I want you to be at 0.05, which is a relative position on the axes, 5% over, and 95% from the bottom. So that's basically saying, forget about my data. I could pan and zoom, and this would not move because this is not in the data coordinate system. And the way you specify that is by setting the transformation. So Matplotlib has every Matplotlib artist has a transform under the hood. The default one is called transdata. It's what turns your data into the figure coordinate system. But the axes coordinate system is 0, 0 is here, and 1, 1 is here. So you can put something anywhere in your figure in that coordinate system just by saying use the axes coordinate system. So that's what a standard text would look like. But if you want to decorate it a little bit, you can pass in this dictionary of properties. And these are properties from Matplotlib patches. They have face colors, edge colors, alphas, and essentially a style. So this, I'm going to use a round style with a wheat face color and an alpha of 0.5. So you basically pass in this dictionary to what's called the B box. It's the bounding box of your text. Props. And then you can do something like that. Turns out we have a number of styles. So, you know, if you like the postage stamp look or something like that, there's a number of styles that you can use. And if you do a help on all of this stuff comes in Matplotlib patch. The patch is the abstraction of a 2D area. So basically Matplotlib has a line as a base class and a patch as a base class. So rectangles, polygons, ellipses, all of that stuff is a patch. So if you want to see the different box styles that are out there, left arrow, right arrow, round. We've looked at round and sawtooth. These things also have optional parameters that you can pass in. So I'm going to just use a different one, like a right arrow is a different style we can use. Yeah, there are various things, and you can control some padding and things like that. So again, this is the work of our friend JJ. Since we're out of time, I'm just going to highlight some stuff you may have seen. We have a lot of support for annotations. So basically an annotation is I want some text to point to something in my figure. And you can each one of these things, there's basically the point you want to annotate is xy. So here, I'm annotating this point at 2 minus 1. And my text also has an xy location. So very simply, those are two different things. But what we support is the ability to specify those coordinate systems in many different ways. So here, for example, my xy coordinates are data. That's your standard data coordinate system that you're used to working in. But you can specify your xy in data. If you want, you can say in data, I want my text to be here. Or you can say I want it to be an offset from my data in points. So points are printer 72 points per inch. This is basically saying 100 points to the left and 60 points above. So it's just a relative physical position to your data. That's where you want your text to live. And then you can connect your annotation with an arrow. And there's a lot of arrow styles. So this is a fancy arrow. It's got a face color of 0.6, that's gray, an edge color of none, so there's no edge color. Basically, we're connecting to this ellipse. So rather than the center of the ellipse that we're annotating is actually here. That's the point it's annotating. But we're informing it, you're annotating this ellipse, so just point to the edge of the ellipse. So you can actually tell it the physical, even though you're annotating a coordinate system, you can tell it the shape of the thing that it's annotating, and it will look at where that is and make sure it doesn't go inside it. So there's a lot of things you can do there with connection styles. I mean, this is again JJ stuff. I'll just show you without, if I don't, for example, tell it what that patch looks like, it goes into the center. And I can say I want this to be at minus 60, which would be below, and it comes in from below. So there's a lot of ways of specifying annotations there. These are just two other examples showing you the kinds of things you can do. And I'm going to call it quits because we're just over 3 o'clock. But the last thing in this worksheet is how to create your own color mapping. So if you want to write, we probably have hundreds of color maps inside Matplotlib. If you want to write your own, it's here. One of the things Paul's interested in working on, and we might even have a Google Summer of Code, is writing a color map editing tool. You've probably seen these things in like Adobe Photoshop where you can drag the segments to show the RGB of the color mapping. We want to write a tool like that using the Matplotlib event handling so we can deploy it across platforms.